My name is Luke Francel, and today I'm going to be talking about integrating Rust and Go, and some lessons we learned doing that with GitHub Code Search. If you've used GitHub Code Search in the last decade or so, you may have noticed that it wasn't that great. It had a lot of limitations on what you could search for, and it was really slow. So my team is the team that was responsible for trying to fix that. And we did it by building a new search engine from scratch, designed specifically for searching code at large scale. It supports, we call it Blackbird, and it supports exact substring match, regular expressions, and code navigation like jump to definition. And it's fast. You can search across billions of files on GitHub and millions of repositories in just a few hundred milliseconds. And of course, it's written in Rust. Otherwise, I probably wouldn't be talking to you today. But in fact, Rust is really great for search engines. It's high performance. It has good concurrency support. We especially love using Rayon. When we need to do asynchronous tasks, we have access to great libraries like Tokyo. And we have complete control over memory management. That's really important when we want to keep our queries per second steady and not have big latency spikes due to garbage collection. And there's a lot of terrific libraries in the Crates ecosystem that help us build search tools. So we decided to build this search engine with Rust. But GitHub doesn't use a lot of Rust. If you look at GitHub's architecture at a super high level, it looks kind of like this. We have github.com, which we call internally GitHub. It's a 15-year-old giant monolithic Rails application written in Ruby. And there's hundreds of developers every day who contribute code to this repository. However, more and more services are being written external to the monolith using two methods. The first is RPC, or Remote Procedure Call. We use the Twitch TV library twerp to do this. And these external services are typically written in Ruby or increasingly Go. The other way is through asynchronous workers that consume messages over a message bus. In our case, we use Kafka. So the monolith will publish a message when something happens, and then consumers can read those messages and do something with them. So Go is increasingly the choice for these services. And that's because Go is not only high performance, but well supported at GitHub. Our deployment platform supports it out of the box. You get great observability with logging, metrics, exception tracking, and distributed tracing. You get automatically generated RPC clients and servers using that twerp library. And there's lots of GitHub-specific libraries that are written in Go that you can use. But as I said, we decided to write our search engine in Rust. So we need to figure out how are we going to connect this Rust search engine with the rest of the Ruby on Rails and Go ecosystem at GitHub. And it's not as simple as this picture. In fact, each cluster that we have for Blackbird has 32 pieces of the index called shards that all run on separate servers. So we need to connect all of those to be able to do a search and to index content. So how are we going to do that? Well, we didn't want to have to figure out how to get Rust working in this ecosystem while also trying to build a search engine from scratch. So we took the path of building the first version of our system using a Go middleware. For example, our crawler is written in Go. It receives events from the GitHub monolith. For example, when a repository changes, like you push code to your repository. It then asks the Git API, which is also a high-performance Go service, what changed between our prior state of that repository and the current state. And then we go and receive all the files, or all the content that correspond to those changes. And then it does document construction. So this involves marrying repository metadata, like the name of the repository and its ID, with the content that is in the files and the paths, and also stuff like language detection and symbol analysis. Once it builds a document, it publishes it to an output topic, which is consumed by the Blackbird index shards. Querying works similarly. When a request comes into github.com, it will be forwarded to our Blackbird query service, which is also written in Go. and is responsible for fanning out to all of the Blackbird shards and gathering the top results from each and returning the results to the user. It's important to note that because of the way we architected our system, the query service has to get a response from every single shard in order to get a complete search result. If one of these shards is unavailable, we can't serve results. And we'll come back to that point later. As I said, that's a consequence of how we decided to shard our content. And we do that by the blob object ID of the Git blobs. So every piece of content in Git has a unique ID determined entirely by its content. It's a content addressable system. And so when you have a path that's associated with a globally unique piece of content, that's no problem, because that's going to be associated with one path, one piece of content. It's going to be very fast to search. However, if you have a file that's shared across many repositories, they all have the same content, they're all going to map to the same shard, and then we could have a problem. The way that this works internally, or the way it used to work anyway, is that we have our content and then we have a table essentially of metadata, which includes the path and then some information about the file. And this became a problem as we added more and more repositories, because when a search would hit one of these shared content pieces, it would hit this table, and then it would have to scan through that through this list to find the right path to return to the user. And that became really slow. And so we knew that we couldn't launch with that. So we had to come up with a solution. And we call that solution delta compression. The way it works is we look at the similarities between repositories based on their paths and blob tuples, essentially. So if you imagine this example, there's the Torvalds Linux repository, and then maybe GitHub has a fork of it, and it has a couple hundred paths different. And then maybe I have a fork of it, which just has a few paths different. So what we wanted to do with this delta compression is reuse the content from the parent repositories so that we don't have to index everything in the child repositories. To implement this, we needed two new data structures. First of them is called the tree path. This one's fairly simple, but it's just a way of representing this ancestry in a compact binary format. The second one is more complicated. It's the geometric XOR filter. This is a probabilistic data structure that's specialized for computing symmetric set differences. And that's the metric we use for determining how similar a repository is to another repository. If you're familiar with hyperloglog, it's sort of similar to that, but it's more optimized for this set difference case. So we knew we had to write these in Rust to use them in the search engine. But for Go, for the crawler, we had a choice. We could write them in Go, or we could try to share the code. And we decided to share the code for two reasons. First of all, we found that Rust is really great for algorithms because it's safe and fast, and the type system really helps you from making mistakes. Go's type system is not quite so robust. And we thought that it would be less complicated if there was just one implementation. We wouldn't have to worry about bugs that were happening because the Go implementation or the Rust implementation were slightly different from each other. But sharing the code requires using FFI. Both Rust and Go have ways of doing this. In Rust, we have extern C, and in Go, we have CGO. But there's a famous blog post from Dave Chenry in the Go world called CGO is not Go, that kind of enumerates all the weird things you have to deal with when you use CGO. And if I can paraphrase that, I'll say that extern C is not Rust. Of course it is, but all of the great things that you love about Rust, the safety and the types, a lot of that you don't get to use anymore because it's inherently unsafe. In fact, both of these languages have features that we love to help us make robust software systems, both Go and Rust. Well, when you use FFI, you can pretty much forget about all of this stuff. You want to pass a string from a Go program to a Rust program? Forget about it. C doesn't have safe string type, so it just has pointers. So passing objects across that boundary is really complicated. And it's not just strings. Vectors, enums, iterators, all the features that you love in the Rust standard library are really difficult to use across this boundary. My coworker, Jason Orndorff, likes to say that FFI means your favorite features of your programming language are turned off. But we're committed. So how are we going to make this work? Basically, we need to make an FFI sandwich. At the bottom layer, we'll have our Rust API. This will be nice, normal, safe Rust code. And then we have to make an extern C wrapper that exposes those functions to be called from C. Then we have to have headers for linking, and we use cbindgen for that. This is a great crate from Mozilla. On the other side, on the Go side, we'll need to use cgo to create a wrapper to call those extern C functions. And then we have our Go client code. Our first approach with this, we used what I like to call the Go-like API. I call it that because the resulting API was really nice to use. It looked just like normal Go code, but it has some problems, which we'll get into. So I'll just go over briefly the layers of this code and show you how you kind of put them together. So in our Rust code, we have a tree path, which is the static representation of this. It has an array of bytes. And we have the mutable version, which allows you to add IDs to the path. And the tree path version has a method for getting the bytes out. So then we have our extern C wrapper. So we have a function to create a new tree path. We have one for pushing an ID onto it. We have a function for getting the bytes out of it. And because this is C, we need a way of getting rid of it. So we have tree path free to drop the memory. On the Go side of things, first thing we need to do is tell cgo where to find this shared library. So we just have some compiler directives here, and then we import C, and that unlocks the ability to use cgo. The Go code itself, we also have a tree path struct that mirrors the Rust one, but what it has is a pointer to the Rust struct. And that is lowercase, which in Go means that it's unexported. And so that means that nothing else in the program can access this except for the methods on this struct. So we need a function to create the tree path. And because Go is a GC language, we want to set a finalizer to clean up that object when we're done with it. We have our methods calling the the extern C functions to push IDs and to get the bytes out. So here's how you use this API. As I say, looks just like normal Go code. It looks very pleasant to use. You just create a path, and then you can push IDs onto it, and then you can get the bytes out and do something with them, like save it in your database. But astute observers might have noticed a problem with this code. And the problem is right here. So when we use this, we saved the data into our database, and then we read it back out, and it was garbage. What happened? Well, it's classic use after free. We set this finalizer when we created the tree path, and Go's GC decided to run it at some point. And that made our data slice point to random memory. And so it was no longer valid. So finalizers are tricky because you have no control over when they run. The GC decides. I want to be clear that you can make this work, and we did fix this bug. But we ran into a lot of problems trying to make Go and Rust interact this way. Go is a GC language, and Rust wants to track ownership, so it's kind of difficult to get them to play together nicely. So we came up with a second approach, which I call the C-like API, because what we wanted to do is make Go responsible for allocating all the memory. And that way we don't have to worry about Rust freeing it when we didn't want it to. The Go GC will have full awareness of what's going on. I call it the C-like API because what we are changing to is kind of a more low-level API where we pass in pointers and set them in the Rust code. And we have out parameters like in a C program. So the Rust API stays the same, but we need a new approach to the extern C code. So here when we create a tree path, instead of returning a pointer, we actually take in an out parameter and the length, and we allocate that memory and then set it into those parameters. When we push a child, similarly, we have to take the path and the length for the original tree path, then the child we want to push, and then the out parameter and length in order to write the data into that. So the Go code looks like this. We need a function to create a new tree path. And notice that instead of returning a struct now, it's returning a slice of bytes. So this is a little bit less pleasant to work with because we no longer can rely on the type system as much. We are dealing with opaque bytes. Push child also is a function now instead of a method, and it takes the path as bytes. Here's the old API compared to the new API. You can see it's still pretty reasonable to deal with, but data is an opaque type now, and so we just have to, I guess, keep that in our heads instead of in the compiler. So we were pretty happy with the results of this. We were able to scale from our technical preview phase of 6 million repositories to up to 50 million repositories. Meanwhile, we kept the total reindex time down to 24 hours. That's really important to us because we like to be able to experiment with the index format. And we reduced the number of documents that needed to be indexed by a factor of about 2 based on using this delta compression. So overall, we were pretty happy with how this worked out. So as our confidence with FFI grew, we considered a third approach to solve a different scaling problem. To motivate this, let me discuss our approach to dynamic shard assignment. So if you recall when I showed this picture, I said that the Blackbird query service needed to contact every single Blackbird shard in order to make a result. And there was only one shard per host, which meant that if a host went down, we would not be able to serve any queries. That's obviously bad, right? You know that saying that if you're not embarrassed by your software when you launch, you waited too long? This was definitely a case of being embarrassed. It got us to our technical preview phase, but we knew it was not going to be good enough for a GA because we didn't want to get paged and have to recompile the code in order to fix the problem. So the approach we came up with is we call dynamic shard assignment. And to illustrate it, let me show a picture from our admin app. You can see there's 32 shards indicated here. Each one of these little colored boxes indicates a host. So now each host is responsible for 2 different shards. So if we lose a single host, we won't have to take the cluster down. We've also got extra hosts. Rather than having 32 hosts, we now have 38. And those extra 6 hosts are doing maintenance work on the index. And so this sort of goes through a state machine that does this maintenance work and then puts that shard into serving and moves on to the next one. But to do this, we needed to implement basically a distributed consensus system because the caller, the Blackbird query service, needs to have the same picture of the world as the indexer does. And the shards are constantly moving around as they go through this cycle. And we didn't want to implement yet another distributed consensus algorithm. So we actually just leverage what we have already, which is Kafka. We publish the state of the cluster to the Kafka topic periodically, and then the client consumes that and reaches the same picture of what state the cluster is in. But that means that our client now becomes quite complicated. It's doing Kafka consumption. It has HTTP clients to make status requests. It's fanning out requests. It needs to compute a load balance. We use maximum flow to load balance across the cluster, so it needs to compute that. It's just got a lot of stuff in it. So again, we wanted to do it in Rust. And that's why I call our third way of doing this the embedded runtime. Because here, what we are doing is packing a ton of functionality into Rust and then just putting a pointer into a Go struct that has a reference to that object. And so the Go code is really unaware of like all the details that are going on. This thing is starting threads and Kafka consuming and a Tokyo runtime. It's doing a lot of stuff, and Go is completely blissfully unaware. So let's take a look at how this works. In the Rust code, we have a Blackbird client. This is like the top level object that we're going to put onto our Go struct. And it, as you can see, it has a complete Tokyo runtime. And it starts that runtime and starts executing stuff. So this is responsible for bridging between sync and async. Then we have our cluster client. This is the thing that does the dynamic shard assignment. So it's starting the Kafka consumer and running the algorithm for that. And then it has this function, or sorry, method route, which returns the current routes. That is, which hosts do I need to contact for which shard? And this needs to be run before every single search request so that you get the current picture of the world. Our extern C shows how we've kind of combined the first two approaches to FFI. We have this client, which is a pointer, sort of like the first approach. But whenever we get data out of the client, we always have Go allocate that memory. That way we avoid those problems with use after free. And here's briefly the Go code. So you can see the Go client has the pointer to the Blackbird client. It has a function for creating a new client and setting a finalizer. So that cleans up all the resources. And then the routes method calls that client routes method I showed on the last slide after allocating the out parameters, and then it maps those into a Go struct. So as a result, we can and have lost multiple servers in our cluster without incident. We are no longer embarrassed by our static list of host names in the Go code to determine what we need to query. We also, when we launched our technical preview, we were only serving about 5 queries per second. And now we're peaking at over 160 queries per second using this dynamic shard assignment client. Now, of course, that's not because we're using FFI, but it shows that we are able to scale the system using this approach. It hasn't been a bottleneck or a problem in the system at all. So overall, we've been really happy with this approach, and it's enabled us to bring the Blackbird code search experience to general availability on github.com. And now when you use code search on GitHub, you're using all this code that I've shown. So overall, we're happy with our ability to interop between Go and Rust. But we actually plan less Go and Rust interop in the future. And that's because there's going to be less Go code. We are working on porting more and more of the Go middleware code into Rust. And the reason for that is because Blackbird as it exists today is a giant distributed system. It has tons of servers and VMs and Kafka queues and all kinds of things like that. And we need to find a way to bring the code search experience to GitHub's smaller deployments like GitHub Enterprise Server. GitHub Enterprise Server is our on-premise product. And there's just no way that we could fit all of Blackbird into it today. So what we want to do is port all of this code to Rust and then produce a single binary that operates in a smaller mode for that smaller environment. We don't need to scale to hundreds of millions of repositories when we're in GitHub Enterprise Server. So we'll be able to do things a lot simpler. But that'll all be easier if we have one language that we have to deal with. So in conclusion, we have found that Rust is a great language for expressing algorithms and data structures. We feel that the type system helps us feel very confident in our code, and the integrated tests don't hurt either. We've also found that Go and Rust can work together effectively, but the boundary is tricky. We definitely had more success with simpler code where we rely entirely on Go allocating. We've also found that distribution becomes trickier because of shared libraries. One of the things that I love about both Go and Rust is that you can easily make static binaries that are just a snap to deploy. But when you use Go, you're linking in a foreign library, and so you have to figure out a way of packaging that with your code. And this is one of the reasons why a lot of Go programmers don't like Go, honestly. The other problem with distribution is sort of a self-inflicted problem, which is that we use Macs to develop on my team for the most part, and we deploy to Linux. So we have special hacks in our build system to just allow us to run our software locally, which wouldn't be necessary if we weren't doing that. Finally, we found that Rust can land and expand. When Rust was chosen as the programming language for the Blackbird code search prototype, it was a risky choice. There weren't a lot of people at GitHub who knew Rust, and it wasn't supported by our deployment platform, our observability tools, all of that stuff. So it was a big risk to choose it, but because of the success we've had, we have gained confidence in Rust, and we're rewriting more and more of our system into Rust. And other teams at GitHub are now interested in using Rust to solve their problems. All right, thank you for coming to my talk. I'd also like to thank my teammates who work on this with me at GitHub. I'd especially like to thank Greg Orzel, Jason Orendorf, and Timothy Klim, who did a lot of the work to figure out how to get this Go and Rust code working together effectively. Thank you.